Welcome everyone. We are glad to have with us today Dr. Mukherjee from University College London. Bhaskar did his PhD from here in Kolkata at IIC, the Christian Memo, and then he moved to Shanghai in Wincheck Quantum Center at where he did his first postdoc, and then he moved to University College London, where he's currently working. So he works on molecular phenomena in quantum systems. And today is going to give us a talk on quantum anybody stars, which are some special states which, like anybody localized states, evade the notion of convergence. So, Master, please. Yes. So maybe move the mic a bit. Just move your color. Mic. On the side of the phone. It should be. You have to talk a little loud.
Oh, okay. I mean, I can talk louder.
But you could.
Hello? Hello?
But of course, it has to be directed. His face.
Has to be.
Okay.
I think
this is good.
This is bit better.
This is
Bit better.
Okay. Thank you. Okay. So this is probably my first official visit in this institution. As already said, I'm currently a postdoc at UCL London, and the title of my talk is kinetic constraint sufficient to generate quantum many stars? I will explain the meaning of this question and different components. What do I mean by kinetic constraint? What is quantum many stars? And also why this question is interesting, important, and we will see at the end of the talk that we have a definite answer to this question. Okay, so this quantum many star thing was introduced relatively recently. The literature is only 5 years long, but by now there is already 3 big reviews. So if you're more interested, you can just take a look. This big literature. I will start with this experiment because all these things started with this experiment. 51 atom ring per quantum simulator in this paper. So this is Robin many dynamics and a 51 atom quantum simulator. So these are Rydberg atoms, which are highly excited states of this kind of atoms. Highly excited because you can see the factor principal quantum number 70 here. So these are very highly excited bound state. And these are like 2 level. Each of these Rydberg atoms is a 2 level system. So transition from ground to excited. And you can use these lasers to induce transition from the ground to excited states. And when they're in this excited state, Rydberg state, you can also tune interaction between them. And this GIG is of van der Waals form, so it's a long range. Yeah, and there is this delta is called tuning star.
It's the excited state of the nucleus or the electron.
The whole atom.
So yes, most of the component is from the electron part, not the nuclear. But he's right, it's whole atom, so some nuclear component may be there.
Yeah, yeah. Yes, because of this MF factors, maybe some hyperfine or something. Yeah.
So mostly
Yes, from the yeah.
Most contribution is from the electron sector.
This is the principal quantum number.
Nuclear component may be there.
Yeah. There may be coupling or. Okay, so yeah, and so these Rydberg atoms themselves are quantum systems, but using these lasers, many things, many parameters in this Hamiltonian are many properties like transition probabilities or interaction between these Rydberg atoms are so highly tunable that you can simulate another quantum system. Let's say the ground state of this kind of Hamiltonian using this. They are called these, the literature analog quantum simulators. Yeah. So Yes. Okay. So with this thing, if you want in this parameter regime, where the nearest neighbor interaction is larger than this detuning term, larger than this transition amplitude, larger than this next nearest neighbor interaction, the effective low energy description is described by this annotation, where you see that there is a transition term between ground and rebirth state, and just a on-site sort of detuning term. The thing is, this Hamiltonian looks non-interacting, but these RR type of configurations are not allowed. So the constraint Hilbert space is like the compost of states where this RR is not. Two Rydberg atoms cannot sit next to each other. So it's a two-level system where you can identify the ground state as down and the Rydberg state as up. Then two nearest neighbor up is not allowed. Yes, 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 yes.
It's just a spin system.
Yes, yes, yes.
Not two atoms, you can be two atoms nearby, but they can't be both simultaneously excited to the
Yes, yes.
Only one of them can be excited.
Yes.
Especially they can be close. One must be G, one must be R.
Yeah, yeah, yeah. So they call this Rydberg blockade rate. So Rydberg blockade. So since it's matter like 1/6, so in small distance it diverges. It costs a very huge energy if you keep two Rydberg atoms within a Rydberg blockade radius. And I'm excluding those processes. Okay. Now this Hamiltonian has two like the ground state in two limit is known. This limit, the ground state is this Rydberg vacuum phase when all the atoms in the ground state. And in the opposite limit, there is a Dept symmetry broken phase where this RG or nil state. This is basically your nil state on this opposite. So the top row is this ground state, all ground, all atom in the ground state, and this bottom row is in this. It is this ordered state, Dept symmetry broken order, and these intermediate rows are like dominoes. So all these blue oval set things are all dominoes. And so these are two phases, and in the intermediate parameter regime, there is a quantum critical point, second order, yeah, and which you can see by if you just plot the dominoal density variance with this parameter. In the around the intermediate value of nearly 0, there is a spike which signals a quantum critical point, and this was long studied back in theory. Now, what people are interested in the dynamics of this system. So these are just the equilibrium phases. And now we are interested in studying dynamics of this system. So what they did, they are interested in the dynamics. So let's say you prepare your state in this Z2 state. I call it Z2 state. It's just a nil state, if you wish. And then sudden point your parameter delta 2 state. So this part. So here you prepare your system as large.
What's your Z2 state in the current scenario?
So it's just this RG. That
okay, okay, like that. Okay, you're at regular values.
Yeah.
Is it possible to excite like that?
Yeah, so you just excite.
Experimentally, is it possible?
Yes, so I will explain how they are preparing this.
Okay.
So in this opposite, when this delta is large negative number -20, all the atoms in the vacuum state. That's this. But the other limit, the ground state is this RG. So you would like to prepare this state by preparing the state in its down state on opposite limit. So what they do, they quite slowly tune this detuning term from large negative to large positive. Very slowly, because there is a quantum critical point involved in between. If you don't go slowly, you may excite the systems. So in this limit, in the opposite large 20, this state will be prepared because this is the ground state in this limit. And then they suddenly drop it to the deco. You can see in this figure that this is the Rydberg probability. This state has been prepared. This black and dark and white region. This is the that has been prepared by this time. And then you suddenly crunch your parameter to get the decision.
At delta equal to 0, what is the number?
It's not easy. It's just not.
So resolution of finite states or is like multiple levels? Number of states is producing.
Yeah. So it's probably a continuous J margin.
That limit to the
Yeah.
delta is.
So previous one.
No, no, that's
This is the effective.
so this is just like a site energy, or I would say that
Yes.
it's just like a magnetic field.
Yeah, so it looks like a non-interacting because this is just a hopping dump and this is just on-site dump. Yeah, but these configurations are not allowed. So that actually takes care of the interaction. And that constraint is actually taking care of that interaction.
What is the E?
These V's are okay, sorry. Yeah. So these V's are this
Okay, that is the
interaction
pull-up.
potential. It's actually van der Waals. 1/6. That would
So
that
the
would.
form is.
Yeah, yeah, because these atoms are of dipoles. Yeah. Okay. Yeah. Okay. So yeah, the ground state is not easy. There is a variation of course, but it's not easy to write down. Yeah. Yeah. So you observe the subsequent dynamics. Okay. And what you see that this go away easily, which you can see here that it's getting a bit opaque, but it's still there. The order is not finished. So you can see if you plot some quantity like domain or density, then there is this long-lived oscillations. And this was a surprising observation. Why? Because this initial state is an infinite temperature state with respect to the evolving Hamiltonian. Under which the system is evolving. Now, the system is non-integrable and it is expected to satisfy eigenstate normalization hypothesis. So, this state is quickly expected to relax to its infinite, which it doesn't. But why? There is no disorder, so there is no MBL-like mechanism involved here, and it's there is no MBL. This model is non-integrable. Then why this oscillation is so long? Whereas if you start from all vacuum state, like all the atoms in the vacuum state, Rydberg ground state, that state is also at the same energy density, infinite temperature, just like this jet state. That state quickly thermalizes to infinite temperature, and that was actually studied long ago in this paper. So that state display expected behavior, but this doesn't. In spite of the fact that both of them, the energy density of both the states are both at the middle of the spectrum. So yeah, so it is expected to satisfy what then it does not display expected behavior. So people were quite excited about it for some time, and then the quick explanation came in this paper. So I am just writing that Hamiltonian with the delta term fixed to 0 in this manner. So that RR not allowed, that constraint has now been adapted in the form of the Hamiltonian by putting these projectors on two sides of this sequence. Okay, and due to this form, this Hamiltonian is known as PXP. Yeah, and you just identify ground as down and Rydberg as the up state. So then these up type of configurations are not allowed. Okay, and these projectors are just projectors to the down spin, and it takes care of your constraint. And if you just do simulations, numerical simulations with this Hamiltonian, evolve the new state with this Hamiltonian, you will see there is this long-lived oscillation, monochromatic oscillation. And if you just plot the overlap of your initial state with your energy eigenstate, then you will see this structure. There is this spikes surrounded by these red squares. These are known as quantum many-body scars, and they have regular energy separations, and that is very closely equal to this frequency. So these states are called quantum many-body scars because these are many-body interacting systems. These are just finite energy density states with low entanglement, or maybe more precisely, logarithmic area or logarithmic scaling. Hence, they violate CTAs. So these are like weak violations of ETAs because these are only, their number is very few. So the number scales here as L, right? The bulk of the states, they all satisfy. So this is only a weak breaking of Edward system. Okay, that was a nice question there.
Why the star and why they
Okay, why there's okay. So there is a long literature in classical physics in single particle quantum mechanics. They used to call it quantum stars. So these are now just quantum many body stars, but there are papers in 1984 even on quantum single particle quantum stars. So these are just unstable periodic trajectory of some specific kind of potential. For example, if you take it, they call it minimum stellium, particle and some specific direction, you will see it will keep on bouncing from different worlds. And if you solve the corresponding quantum problem, you will see there are eigenstates which are localized on those trajectories. So they used to call it quantum single particle. And just in exact analogy, if you just start from the specific initial state, just like those specific initial directions, you will see this star-induced oscillation, not from all other initials. So, for example, this vacuum state that quickly normalized, as I said. So it's a very highly initial state dependent. All the rest of the states are found.
Yes, sir. So, these two scales are there. Of course, there is a decay scale. Like there is a decay, right? The amplitude decay.
Yes, yes,
Scale
yes.
associated with amplitude decay.
Yes.
And there is also a frequency.
Yeah.
Time scale associated with frequency.
Yeah.
Have people identified, or maybe you will mention what does these two scales correspond to?
This is a bit difficult. Maybe. This bigger one. This is a bit difficult.
What about the oscillation scale? Frequency.
Yeah, this lower one is this frequency.
But what is the model? What should I understand this frequency?
Okay. So this will be okay.
Usually in single particle, it is some sort of gap, energy gap.
Yeah.
So Rabi oscillations or whatever.
Yeah.
What would that correspond to?
Oh, so you see in the Hamilton there is only one scale, which is this omega. And your energy gap here, which is delta 3.7.
So I should understand these as separation between parts.
Yes, exactly. So this 3.72, if you look at it, it's nearly also 3.7. So this is the energy gap we discussed. Yeah, but the longer
So it's doing some Rabi oscillation between stars.
Yes, yeah. There's interpretation like that.
What is the unity Z symmetry by size? So are you searching for Niels state out of the that log of Z to sim by size? So what that Z to sim by size is?
Oh, yes. Okay. So to do exact diagonalization, you can use symmetry sectors. And if you do that, you can do a very large systems. So I use a symmetric linear superposition of nil and anti-nils that allow you to go very large system sizes, but it's fine. It's just the nil kind of order.
By writing Z to sim, you are actually looking for the Niels states.
Yeah, nil and anti-nil, so up, down, and down, up. Just go.
I mean, getting the higher values at some particular V value, you are building that those to be stars. So your criteria to have a stars like to have some Niels state. Right?
In the PXP model, it's like that. So the star states all have large overlap with the nil states.
Remains not generalizing. Okay.
Yes.
Right. So that is basically log of the overlap with the initial state. So it remembers the initial state. That's the end.
Yeah.
That is means it's not.
Okay, so what are the further motivations? And there was actually an explosion of works after that, after this experimental and this first theoretical paper. And then it was found in a lot of other models, like again, these T1XY Hubbard model, some dimer models. And in most of these models, people can construct these star states exactly. So you can write down the exact expression of them. So they exist even in the sound dynamic. There's a related closed SL2 algebra. I will not go into the detail, but after the talk, if you're interested. So these are all well understood because of this exact nature of the states and also this SL2. But what about PXP-like constant model? It's an irony that in spite of being the first model of quantum star, both experimentally and theoretically, the mechanism of scarring in this model is ill understood compared to this model till now. Yeah, but okay. So I will briefly tell the corresponding literature. So there is only a few exact states. This paper, only one state is exact. But you saw that there are roughly L number of states. So there is only semi-analytical kind of method exists because this is a non-integrable model. So all these methods like forward scattering approximation, single mode approximation, time-dependent variational principle, possible picture, they're all kind of semi-analytical at the end of the day. But you can push the system size with these sort of things up to some longer values. But SUT algebra is never exact. I mean, Either you start from the nil state or from the PXP ground state. SUP algebra is never exact. So that and since the states are not exact, what is the thermodynamic limit? That question was in there for some time. Recently there is some work, but not fully settled. Yeah, since the states are not exactly known, so what is the fate of these dynamics in the thermodynamic limit? That has been an open question. So what is the mechanism of scarring in this sort of PXP-like constraint, and what role constraints play? Okay, so we will try to understand this. So there is little scope in spin-half PXP model to understand. Why? Because if you just remove this constraint, which is just equivalent to remove just these projectors, this will boils down to this, which is a very trivial collection of free particles. At most describe a free parameter into a gas. So the problem is, okay, so the constraint is the interaction between two nearby Rydberg atoms, which also at the same time make the model non-integrable and ergodic. On the other hand, these constraints are also believed to be responsible for this scarring. Now this is a weird situation. Now the same ingredient actually is which is responsible for both making the model ergodic and also scarring, which are two competing phenomena. Yes, so that was a problematic situation. So there was little scope in spin-half PXP. So that's why we asked the question that what about higher strain PXP? I mean, can we address this question? I mean, the interconnection of this kinetic constraint and scarring. This interconnection, can we, answer this question relatively in a better manner in higher strain PXP model? Because there the local degrees of freedom is high, so that may be an ideal platform to answer this sort of question. How I will explain. Okay, so before that, let me just briefly mention what is spin-S PXP model. This is the general form of spin-S PXP model because of this form. So it's PXP. And local Hilbert space is just spanned by the eigenstate of this SZ operator. These projectors are of this form, like this PAs are this. You can convince yourself that why this is so by just comparing with the spin-half case. But this form holds for any spin-S. It boils down to the spin-half form. You just put spin-half here. And so, for example, this constraint means that at least any of two consecutive spin must be in the lowest eigenstate of this. So, for example, in P1, all these four configurations are not allowed. Okay, that this projector means. So the constraint Hilbert space is spanned by configurations which does not consist of this type of configurations. Okay, that is plus 0 minus and plus SZ. Okay, now this was actually studied. This also hosts J2 stars and exhibit elongate J2 oscillation, just like spin-half PXP. So I will call this thing the traditional spin-1 PXP model for this form. And now we will do constant engineering. Like out of these four configurations here, we realize that we don't need to have all this. We don't need to disallow all these four configurations. We can selectively choose any number of them and can write down PXP Hamiltonian of the same form by choosing any of these or many of these constraints. So, for example, what happens when different constraints are used? So, for example, I am constructing three models, three spin-1 PXP models, model 1, model 2, and model 3, by just removing configurations like this. So, for example, let's in these two limits, this spin-1 free parameter and in the opposite limit, this is just the I call it traditional spin-1 PXP model. Just I said, as I said in the last slide. So if you just there nothing is allowed. Everything is allowed. So this is 3 to the power n. Now, if you just remove this configuration, this type of configurations, you end up in model 1. Which, if you further remove plus type of configurations, you end up in the traditional spin. Model 2 is when you just remove the 0 type of configurations, and model 3 is when you remove both 0 and plus type. Now, let me mention that this was purely of academic interest and mostly inspired by the question that how kinetic constraint and quantum scarring phenomena is interconnected. It may be a bit difficult to tell how to realize these Hamiltonians. But yeah. So I will describe the properties of this three model briefly, and we will see that how what constant engineering can do, and on this way you will get an answer of the question that was asked.
So when you are excluding, so you're excluding those plus zero, zero plus kind of thing,
Yeah.
you are using some Hamiltonian or by looking at the configuration or just
Yeah. Okay. So if you ask like how do you
let us say we are dealing with a large system, they cannot do by distribution.
yeah, I mean, you can of course write down this.
Okay.
So you just so the Hamiltonian is just this SX term actually in the corresponding constant Hilbert
It
space.
is a parameter.
So if you just generate the constant Hilbert space by just removing this type of configurations, in that space you just write down this SX term, sum over SX. That's your Hamiltonian. So numerically it's straightforward. Yeah. Yeah, but it's difficult to tell what will be the property of the spectrum of those Hamiltonians, like this one model one. Okay, I'll briefly tell. So model one exhibits Hilbert space fragments. So these three configurations are not allowed, but plus plus is allowed. The Hilbert space dimension is this, which you can. This is an analytical number, not a numerical number. You can calculate this using transfer matrix formalism. The projector is of this form, which is not very important. The important thing is this Hamiltonian is actually host a lot of exponentially many number of dynamically disconnected sectors. So in the x-axis, so there are this number of dynamically disconnected sector. In the y-axis, the number of states in those sectors. Okay, and HPXP, which I note by this.
What is conjugal?
These are blocks, so nothing is comes up. So this is not caused by any symmetry. So this is actually beyond symmetry related. That's why they call it Hilbert space fragmentation. I mean, this is a sort of this is a constraint induced. They appear for other mechanisms. I mean, there are other mechanisms as well. Factors or
Something which takes that.
yeah. So these are blocks. So for example, these are just 1 cross 1 blocks, like, and these are maybe 3 cross 3 blocks, and their size is increasing. Size of the blocks are increasing. All the states in a specific block they are interconnected, but states in the different blocks they are not connected by that. It's just like block diagonalization.
That means it's some symmetry.
Yeah. Naively you expect symmetry, but we tried. It's difficult because their number is exponential. And
Because your SX is just a slight dependent. It's not even connected. None of these things. Okay, oh no, you have the B and
these projectors actually takes care of that.
this is not just a simple SX.
This is an interacting manivodian. Yeah. Because of this constraint.
Inside each of these blocks, is simple SX. Inside each of these blocks is simple SX.
This operation is taking you to different tests.
Exactly. Different, yes, projectors.
No, SX is fine. But thing is, distant
What are the
symmetry
what are the
may
states?
develop.
What characters?
So these constraints, yes. So,
It's a group of
so in each of these blocks,
So there will be
Correct. So there should be some symmetry which is preserved because it's something which is very unique.
yes. Okay. So naively what I can this is a clean model. So naively there is translation symmetry and there is inversion symmetry. But these are not because of that. And you can just restrict translation and inversion. Even in that sector, let's say zero momentum and inversion symmetry sector, you will see further block diagonalization like this.
But it's getting separated out. That's
Yeah.
what makes me
Exactly.
like some hidden symmetry.
Exactly. That's a very yeah. I think that's quite a common expectation. Actually. We also expected that, and I will tell you, we tried to construct them, actually, but I will tell you the problem. Okay, so the size of this traditional spin one PXP is like that scale has 2 people, but this Hilbert space of this H1 is like this. So it's only dynamically disconnected. Is almost the second largest fragment of this whole model. And this one, you know that in this model plus plus is also absent. So, but I didn't forbid it in the first place. Here it's plus plus is allowed, but here in the in its spectrum, a separate block is appearing where no plus plus configuration can arise. So it's sort of emergent kinetic constraint. So this is known as strong Hilbert space fragment system because the size of this largest subsector here, that's actually a very, even that is actually a vanishingly small fraction of the entire Hilbert space dimension in the timeline. That's why it's a strong fragment system. Okay, so this 1 cross 1 block. So this means these are just eigenstates. So these are very simple states like this. I mean, which is very trivial to see that why they are just zero energy eigenstates of the Hamiltonian. Because once you add the Hamiltonian on this type of states, the states get annihilated because of the constraints.
So within each block, so your projectors are dimensional blocks from subspaces.
Yes.
Projectors.
Yeah. Yeah.
Within each subspace, the Hamiltonian behaves as physics.
So the projectors only takes care of that this type of configurations are not. That's the subspace on which the projectors are projecting your. Yeah. And now there is a further and yeah. So you see, this size is all not 3 to the power. I believe it should be 3 to the power.
But no, but all projectors may not be independent. All the I projectors may not be independent. I don't know. It may be, but I'm saying.
Sorry. So this P is actually a product over all this as I.
Yeah. So that's what I'm saying. The projectors.
So this P here is actually a product over this I plus. Sorry.
No, that's okay.
Yeah.
I'm saying that all these projectors that you have defined, right?
Yes.
They may not be all independent. That could give you that 0.47 to the power L. Right. So what I'm trying to say is that if you give me n projectors, n plus 1 projector is already determined.
Yeah. I mean, we calculate this dimension actually in a way something like that, as you said. That if you know all the states in a L side system, I can construct the states in a L plus 1 side system directly. So, and that transformative formalism actually gives you this number.
So these sectors would be what? The eigenstates of projector or something.
Yes. Yeah. Exactly. So yes. So yeah. So yes. So in the constant Hilbert space where this type of configurations are not there, it is just a section. Sum over I section. To numerically speaking. Numerically, you just implement sum over I SXI in this constraint Hilbert space. Yeah. But if you look at the structure of that it is by this matrix, you will see they are not all connected. There is this block structure, which is not quite apparent maybe from the form of the Hamiltonian.
No, but the block structure is obvious, right? Because you have PN on both sides.
For example,
You are not allowed to cross sectors.
so in the spin half X model, this is also of this form, but there is no such block structure.
Spin half is integrated.
The spin half X model is also not.
Spin half is
And this is not, yeah, that's what I am emphasizing here. That this is not caused by any symmetry related thing.
no, symmetry. I'm not doing the symmetry. I'm just trying to understand this. How do I, from the projector's perspective, how do I understand each of this?
Okay, I will explain. Okay. Just give me. Yeah. So okay. So these are the inert states. I mean, it's easy to see that if you just act the Hamiltonian on these configurations, they just annihilate those states. So these are very simple eigenstate of the Hamiltonian. So for example, if you act the Hamiltonian, you cannot raise this minus to 0 because plus 0 is not allowed. You can also cannot make this plus down to 0 because 0 plus is not allowed. So that's why all these states are annihilated by the Hamiltonian. So they are zero energy eigenstates, and there are these such states. Okay, and we can exactly also count their numbers. These are the exact expression of the number of such states, both in open and periodic boundary condition in terms of the golden ratio. Okay, so the higher dimensional fragments here, like these, they can be constructed by just appending active sites with these states. So, for example, you can just add minus here. Keep on add minus here. You cannot blindly add 0 or plus. You have to think what is the last site, what is the configuration of the last site. Yeah. So if the last site is plus or 0, you cannot append blindly plus or 0 here. But you can append minus 0 or minus plus. So this goes on in this way. And by appending sites like this, you can actually construct these higher dimensional fragments. and we will gradually approach with these higher dimensional fragments. And I will explain what is the properties of these different smaller size fragments.
What is how are you identifying states in the same subset?
Within the same subset.
Yeah, because you have number of states in subsector in y-axis, right?
Hmm.
So how are you doing that? How are you identifying? So if I understand your entire universe space has got fragmented into various subsectors.
Yes.
What is common between states inside one subsector?
Okay. Okay. So, for example, let's put a minus in between these two minus. Okay. Then that minus is an active side. You can make that minus to both plus or no, sorry. You can raise that minus to 0 or plus, because the both on the neighboring sides this is minus, so you can raise that minus to 0 as well as plus. So now those states are connected. So that gives you a three-dimensional space with a minus in between here and a 0 in between here and a plus in between. So that can give you this. These are all 3x3 blocks.
No, so
Okay.
is the statement like this? States, if I take two states within particular subsector,
Yeah.
the matrix element of H between these two is non-zero.
Yes. Yes. Okay, so there are fragments of different sizes, as you can see. So there are some very small fragments as well as there are fragments whose size scales exponentially. Now let's look at the fragments whose size scales linearly. Let's say, and they have eigenstates with integer energy and magnetization. For example, states with like this, their expression can be exactly found with these IMs, and that since they are exactly known, their properties like Hapton entanglement can also be exactly calculated. So, for example, these are area loss states in the thermodynamics. As you can see, it looks long, but it's constant. These are area loss states. You can get states with energy plus minus 2 as well of this form with these definitions. And if you calculate, you can exactly calculate entanglement entropy of the states, and this scales as logarithmic. So these are plus minus 2 energy states are logarithmically scaling entangled, and plus minus 1 and 0 are area law entangled. Yeah, you can do things like this, and I will also show you why pH is clearly high. So you can also exactly calculate the magnetism of the states. And if this is E equals to plus minus n, is magnetism is n minus 5. It's always positive because this states it does not appear as long as n is less than 5. So these numbers are always positive. And if you calculate now the thermally expected average values, and you will see that this dotted line here of this quantity Sz is actually the thermal expectation values, and they are always negative. Whereas magnetization of these states here, they are always positive. So it is clearly high. And their entanglement entropy here, you can also see that their states is a log and these are area law entangled with the thermodynamic limit. So it's linearly, it is decreasing, but it gets saturated. Yeah. Okay. So now you're coming to your question that what are the conserved quantities? So you see, you can think of conserved quantities like this. So okay. So projected on the eigenstates are always conserved. But here the thing is here the eigenstates can be quite of this form, not very. These are product states. So it's a projected on the product states. So this type of quantities can be constructed and these are conserved. And you can imagine to label these fragments with these numbers. So for example, here I have labeled. You can see that this is n plus plus equals to 0, which means this is this traditional spin on bits. And then there is n plus plus 1 greater than 1 and everything. Problem is, for example, with this example, there are 3 fragments with these quantum numbers, which you may wish to further label by this set of quantum numbers. But the problem is you cannot do it, for example, L equals to 3 of this is no longer possible. Because there are more than 3 fragments with this set of quantum. So you need more quantum. And you can see here that they are getting more and more non-local right now. These are now projectors on the string is increasing. So they are getting more and more non-local. So there is no notion of local conserved quantities to label all these fragments. Recently there are some more. This SEM paper by Coleman, this committed as a picture by Sanjay. So we used to believe that there is no unique set of local conserved quantities to label all the fragments. This is still a bit true, but there are some construction like statistically localized integral of motion which you can construct two level, but these are some advanced things which I will not go into the detail. Model 2. Model 2 is a very funny kind of model. Only 0 type of configurations are forbidden. Again, this has this PXP form. These projectors are of this form. Universal dimension has a very nice analytical structure, which is again like scales as this. Interesting thing is that this model has an extensive number of conserved quantities, local conserved quantities, which is this operator. It's a very simple operator, but this, the commutator of this all OIs with the Hamiltonian is for all. So there is extensive number of local conserved quantities. And naively, we used to think that the existence of extensive number of local conserved quantities is almost synonymous with the existence of integrability in the system. It's a nice picture, but here this model is not integrable in spite of the presence of extensive number of local. Why? How to see this? It's very easy to see. The eigenvalues of OI, there is a degeneration. This is +1, +1, and -1. So in total, so from each side you have two quantum numbers, +1 and -1. So on L sides you have 2 to the power L number of available quantum numbers, but you have this number of states. So you cannot level all the states by, you cannot uniquely level all the states by your quantum numbers, by your available quantum numbers. So what you can do, you can at most block diagonalize again. So even extensive number of conserved quantities may not be sufficient to make the model. This was actually, I was not aware of this development, but in Bhaskar system they also see similar. It's nice to see that even from just constant engineering you can realize this sort of things. And these are the eigenstates of O with these things. And again, the largest symmetry sector here is when all the OI are +1. When all the OI are -1, that's a unique eigenstate. And if there is some of the sides are OI equals to +1, those are larger symmetry sectors. And when all the OI are +1, that's the largest sectors. And it will be, and if you identify the down state with O+1 and the up state with O+2, you will see that this largest sector exactly maps to spin half PXP model. So you start with the spin 1, special kind of spin 1 PXP model, and you can get spin half PXP model as the largest sectors. So then many states can be constructed. As I mentioned before, by linear monotonically constructed one exact eigenstate in spin half PXP model. Now we can construct actually many eigenstates in the trivial manner in this symmetry. So is this the sequence of minus and plus defines the symmetry sectors, and these blocks are of PXP model, and these intermediate minuses are just one state, so one single state. So these are like, yeah. So you can construct many exact eigenstates in this. These are just MPS form. Never mind these things. These are just to tell you that exact form of many eigenstates can be written down. Okay, so this is the Hudson entanglement entropy plot. In this model, you can see that there is lots of low integral states. What I want to emphasize, this model 3 is most interesting from the perspective of the initial question that we asked in our title slide. That is kinetic constant sufficient to generate quantum mechanics? Model 3 is strongly agreed, in spite of having that this type of configurations are not allowed. So it's constrained, but as you will see with this form of a projector, this is again a PXP model. Universal dimension again has a form. But if you look at the Hudson entanglement plot, you will see there is no finite energy density low intensity. A sharp parabolic feature is actually signaling that this model is strongly ergodic. We have also calculated this ETH line, this dot test line, which also almost coincides with the exact numerical expectation. So which suggests that this model satisfies eigenstate parallelism hypothesis and it's strongly ergodic. This was a surprising finding at that time, because for a long time people believed that this kinetic constant, as long as you put this kinetic constant, these are responsible for scattering. But as we find out here that it may not be so. Okay, I will come to the conclusion later as well. So we also studied dynamics in these models using forward scattering approximation and everything. So, for example, in model 1, the Z2 state belongs to the traditional spinor PXP block, the second largest block. So that dynamics was actually studied in the previous module, but you can study dynamics in other fragments as well. Model 2 dynamics is quite interesting because you can break the initial state Z2 state in terms of these, these integrals of motions, where this plus are blocks of spin-off PX model, and this intermediate, these are all minor, these are all non-interactive. Due to the projection, as we identified the down state in the O+1 and the up state in the O+2, you will see that these PX2 blocks will rapidly thermalize, whereas these intermediate blocks will. So that, and also there are symmetry sectors which are fully non-interactive, as long as there is no two neighboring O+. Okay, they will exhibit under process. The number of such sectors again scales as 5 L. So the whole dynamics is actually a mixture of strongly ergodic and totally non-interactive. Why strongly ergodic? Because if you remember in the vacuum state, from vacuum state in spin-up PXP model, the dynamics fully thermalized. There are symmetry sectors where it's rapidly thermalizing, whereas there are symmetry sectors where it's completely undamped oscillations. So it's quite interesting to explore the full dynamics of the system. And in model 3, the initial state is strongly connected with all other states in the universe, which is this. This is the universe's connectivity graph of model 3. But this is for model 1 and this is for model 2. You can see that there is these fragments. This is fragmented. Yeah. So all the configurations are connected to each other, either directly or indirectly, which does not occur for. This feature is actually making it strongly ergodic, and the dynamics is
C is strong.
C, the model 3, C is model 3, which is strongly ergodic because of this full connection.
And A is what?
A is model 1, which is reverse fragmented, and B is model 2, which has this extensive number of symmetries.
So what was the difference between so extensive number is not what dynamics? What was the difference?
Okay.
So I can see the extensive number of
anyway,
maybe.
This is the dynamics from the new state for model 1 to 3. So in 3 you can see it's quickly thermalizes. The entanglement or on local observables, they get steady state quite good. For model 1, it depends from which fragments you are starting. So for example, if you start, the new state belongs to the traditional spin-1 block, which keeps on oscillating, the blue color. Whereas for model 2, it's really very complicated. You have to consider all 2 to the power L number of symmetry sector to analytically tell anything about that. Yeah. So the model 2 is somewhat in between model 1 and model 3. Yeah. I mean, you can use this forward scattering approximation framework to say something about this thing. So these are the forward scattering approximation. You break them into 2 parts, which are adjoint to each other. You choose them such that your initial state is annihilated with state 2, and you just keep on acting this H up plus, which is the adjoint on the states and generate this. So this is a Krylov method, and these errors, so there is a difference. So if there is the shift algebra is exactly this quantity completion. I mean, naively in any interacting system, these quantities are always non-zero. That gives you damping force to your dynamics. Here we have found that it's become non-zero only at the 5th state in model 1. We have exact expression for this. For model 3, for model 2, it becomes non-zero at step 3, and for model 3, it becomes non-zero at step 2. All of the previous steps are 0. Okay, and the total errors, so sum over, you just put a sum over n here. That's actually, that quantity is actually effectively given to a damping force. So that's like how quickly your dynamics damps and you achieve a steady state. So you see that these damping forces are largest in model 3 and smallest in model 1. So you can try to understand the dynamics qualitatively using these frameworks. These are not very important. So the study was published in this work. So I will just conclude. So constant engineering can lead to varieties of ergodicity, as I explained to you. Though most of the constant leads to ergodicity breaking of various degrees, like model 1 and model 2, there exists certain constant which leads to strong ergodicity, like model 3. So this allows us to identify constraints whose role is just to produce quantum scar and thus make an otherwise ergodic system and non-ergodic. Because for quantum scarring, you see that you need a thermal background, and then you embed a few athermal states. On the spin half PXP model, this both making the model interacting and ergodic and scarring, the single constant was responsible for the both. It was a difficult situation, but here we know constants which are responsible for only making the system ergodic, because constraint means interaction, and interaction makes things ergodic. So, for example, model 3, that's ergodic, and you know the corresponding constraint. Now, if you just add disallow plus plus type of configuration from model 3, you go to model 1. So you know the role of that particular constant, that okay, this type of constants are responsible for producing stars, which you could not do in spin half Hz. Yeah, so now you get the answer of the question that we posed in the title slide, that is kinetic constant sufficient to generate quantum many-body stars? The answer is no. There are certain type of kinetic constant which may not be sufficient to produce quantum many-body stars. They can make the system only fully ergodic. The opposite way. Yeah. Now, what is the class of such general class of such constraint in spin SPXT model? That's still an open question, like this. That's still not classified. This is just a spin one numerical study. So this is actually, at the end of the day, it's numerical, so you cannot go to higher spin. Sizes of the base increases, and with numerical exact analysis is limited. Yeah, it's a difficult question, but I would like to address it. With this, I would like to. This is my favorite slide. I have come to it. So the field is now going in many directions. It's really very colorful. Out of colors. So yeah, and with this, I would like to thank you for it.
Yeah, question.
Model 2, why are you getting degeneration in the quantum number you are getting? Plus 1, plus 1. Can you please explain why you are getting?
Okay, so these quantities, if you calculate the commutator of this with the which this is, so these are conserved quantities. Now, if you just diagonalize this, this is just a 3 cross 3 matrix. So it has 3 eigenvalues, which are plus 1, and 1. Now, the eigenvalues of the conserved quantities gives you the quantum numbers, right? So these numbers are your quantum number, and now this is a many body. So you have, so from each side you have 2 quantum numbers, plus 1 and minus.
My question is, you are not getting that degeneration for model 1 and model 3.
Yes.
But for model.
Yeah, because in model 1 or model 3, you do not have this conserved. They do not, this quantity do not commute with HI or HG. This is this particular choice of constraint that gives rise to this concept. We actually were doing blind numerics model. And even after restricting the most obvious symmetries like translation and inversion, we found still there are a lot of degeneracies. It should not be in any non-integrable model. That's why we are looking for, I mean, even the spectral statistics was poisoned, even after resolving symmetries. So that suggests that it's an integrable model, because Poissonian level statistics means integrability. But that may not be a sufficient criteria. One should construct an extensive number of integrals of motion, claim the model is integrable or not. That's a typical expectation. But we found actually extensive number of local numbers, which are this. But in spite of this, the model is not because of this.
What is your definition of so if you make it synonymous with if he has extensively large number of local conserved quantities, then I agree.
Yeah.
But if you pose the question from a dynamical perspective, then yes, integrability is taking that is not equilibrium in that sense.
To any thermal grid sensor.
Exactly.
Right?
Exactly.
Yeah.
It can be generalized reasons.
Yes. Exactly. Yeah. Or another thing is, if you can uniquely label all the eigenstates by, for example,
No, that is what I'm saying. So if you say, so what is very clear, having extensive, so you can have conserved quantities without symmetries. You can have conserved quantities without symmetries.
Yes, okay.
That is exactly what you were telling us. You have extensive number of conserved quantities, but there are no symmetries. Constraints leads to conserved quantities.
Yeah.
Right. So in that sense, so should we now define only from the perspective of conserved quantities alone, not talking in terms of symmetry or talking in terms of constraints?
Yeah.
Only talking in terms of local conserved quantity. Local conserved quantity is scaled in a certain way, or if you can, like you were saying, uniquely label all states
Yeah.
with local conserved quantity.
Yeah. Yeah.
Then we will define integrable and non-integrable.
Yes, yes. So, for example, in terms of spilling, it's fully integrable, and there the conserved quantities are this doubling good particular number, which can be either 0 or 1.
Right.
Now you have to discard a eigenstone, it's the same model,
Right.
and bubble on each side, bubble particle can be either 0 or 1. Not in each side, but in every momenta. So it has L number of momenta as well. So that can be 0 or 1. So that means you have two quantum numbers from each K mode, and there are L number of K modes. The total available quantum number is 2 to the power L. And you have also 2 to the power L many body eigenstates in the system. So you can use them to uniquely level all the eigenstates. So here you cannot do.
So if you can't do that, then you are saying
Then
that it can still, there is a chance it is non-integrable. It is
No.
ergot.
If you can do that, then I think that's the most precise statement of it.
So that's what I'm saying. So if you can label uniquely all states with conserved quantities,
Yes, local
right?
conserved
Local conserved quantities, then you will say that it's integrable.
quantity.
If you cannot label, even if conserved quantities exist, we scale with them,
Yes,
there is a chance it's non-integrable.
it's can be.
But it's not guaranteed it will be non-integrable. There is a chance.
Yes, yes. Sure, sure. So, for example, it could be that this largest sector here could also be integrable. But since we identified that this is just a spin-up PXP model, and we know spin-up PXP model is non-integrable, so the answer is model 2 is also not. Because it has at least one fragment, one sector, symmetry sector, which is not integrable. So, on total, it's not.
Any more questions?
So you can show that picture where you are showing model 1, 2, 3 connectivity. You are showing. Yeah. Are those outliers or something, or coming from some other subsector?
Yeah.
Model 1 and model 2.
Yeah. So for model 1, these are okay. So this is for a very small system size like L equals 4 bit. Okay. So these singles are those inert states. If you remember, those single states with 1 cross 1 blocks. If you remember. For model 2, these are different symmetry sectors because we know the symmetry states. This is fragmented. This is symmetry sectors. And model 3 is fully done. There is no such single like smaller fragments. Or
I want to ask that these do have different quantum model.
Model 2 has conserved quantities and quantum numbers, but model 1, as we saw, that it tried to construct, but it's getting more and more non-local and also be difficult.
Sorry, should you just check if anybody online there is there who wants
Sure.
to ask a question?
Sure.
Okay, so nobody is there. Okay, fine. So maybe rest of the questions you can ask over Teams if that works for everyone. Okay.
Yeah, yeah.
Okay, so let's again thank the speaker. You know, next talk. He is there.
Yeah, yeah. Think so.
Okay. Okay.
If they have not
Otherwise,
forgotten.
false promise.
But he sounds like
Okay. So, it is now they can